there it is. Eventually what you will find is a tangent line that will match the secant line. So if you are looking at two endpoints and the average rate of change between those two endpoints, well then there should be some sort of x value that you can find within that interval such that the average is equal to the instantaneous, so f prime of some sort of c. So that is what your definition is stating. There that definition is on page 324 of your textbook. And once again, all it's saying is that if you're looking at an interval from A to B, then if you draw a secant line or you calculate the average rate of change between those two endpoints, then you should also be able to find a tangent somewhere on that interval that has that same slope. So it equals the same slope of the tangent, slope of the secant, slope of the tangent, equal. And what value of x that is, that's up to us to calculate. We're going to do problem number 23, and what it asks us to do is look at the function f of x equals x squared over the interval -2 to 1. Hi! So looking at this function in this interval, what we're asked to do is determine whether the mean value theorem can be applied to the function. And if it can be applied, then find all the values of c in the open interval such that f prime of c is equal to the secant line's rate of change. So we're asked to pretty much find for what value of x will the derivative equal the average rate of change. So the first thing that we have to do is find out, does the mean value theorem apply? And to do that, it has to go through two ideas. It first has to be continuous. So when you're looking at this, is it continuous? Well, yes, it's a polynomial, and please remember that polynomials are always continuous. So yes, because it's a polynomial. I'm also going to have to ask myself, is it differentiable over this interval? And part of the definition states that in order for this theorem to work, it has to be differentiable over the interval -2 to 1. And it is the open interval, so keep that in mind. But to do that, you actually have to derive this. You're going to find that it's 2x, and yeah, you could plug in any one of these values within this interval into our function, and you'd get a defined derivative. So you'd get an answer. So therefore, yes, it's differentiable over this whole interval. So now that we know that, what I'm going to start to do is actually calculate this out. I'm in the end trying to find this x value that will get me the same derivative as the average that goes through the endpoints. So when I do that, I'm first going to have to calculate this. So what is f of -2, or I'm sorry, we're going to start with f of 1. What is f of 1 minus f of -2 all over 1 minus -2? What you're going to see is you plug in your 1, you get 1 squared, so it's 1 minus, you plug in your -2, you get -2 squared, so 4 all over, or -2 squared is positive 4, and then 1 minus -2 is just a positive 3. So here we have it. Oh! -3 over 3 equals -1. So what we're going to be asking ourselves is, when does f prime of c equal -1? For what value is this going to be? So I'm going to solve or find out what is the derivative of f first. We're going to get 2x equals -1. Now to actually solve for this, because f prime of x is equal to 2x, we're going to actually find out what value of x will make this true. So just divide both sides by 2, and x equals -1/2. There's our answer. And just to kind of see what this is visually, I hope you know this is just our typical x squared function. So Go 1, up 1. And then we're only going from -1 to 1, so I'm going to actually stop at those x values. 2. So we go over 1. Should have had this drawn. So here we have it. And here was my secant line. And if you try to draw a tangent line that was close to that, okay, we're going to look at number 29. Part A is going to be asking us to graph it on our utility graphing calculator. So you can go ahead and do that, but I do want to kind of just refresh you on how we have done these in the past. It is a rational function, so we can do that. And I'm going to start out with finding any holes. So if you're looking at the graph, the holes would occur where there's a common factor on the top and the bottom. What you will notice is there are no common factors. So what I have to say for holes are, there are none. Okay, what I'm going to go to next is finding the x-intercepts. So don't forget, x-intercepts are where it crosses the x-axes. So when we're looking at that, you might not know what x value it is, but you do know that all points on the x-axis are where y equals 0. So you would be setting and solving for when this whole thing is equal to 0. That's going to be, of course, when the top is equal to 0, because it's a rational function, 0, because that's when the denominator equals 0, and that's when we get garbage. So we get x is equal to 1. I'm going to go ahead and draw that. Oops, sorry, it should be -1. There is my vertical asymptote. Alright, and then finally, you guys might not recall this, but we will be looking at a different approach in locating the horizontal asymptote soon, but it's what are our end behaviors doing. So what we're going to really be asking ourselves are, what are we going to approach with our end behaviors? And you can find that by that Bobo, Bot, and Eats DC from last year. This would be if the exponents were the bigger on the top, degree was bigger on, bigger on bottom, then y would equal 0. If it was bigger on top, then we would have no horizontal asymptote. But what we're looking at is exponents are the same. So Eats DC, Bobo, Bot, and Eats DC. And this is where we're going to look. We have a degree 1 polynomial on top, degree 1 polynomial on bottom. That's what we're going to use. Our leading coefficients, or our leading terms, are 1x and 1x. So looking at those coefficients, y is equal to 1 divided by 1, y equals 1. I'm going to draw that in here. I'm going to go ahead and plot some points. So now that we have some of our basic, by the way, this is our x and our y-intercept. Alright, these are the plot points that I went ahead and plotted. Sorry, they're a little fuzzy. So here it is plotted. So you could have done all that on your graphing calculator, but what I just went ahead and did was by hand. For part B, what I needed to do was graph the secant line that goes through the two endpoints of my interval. So keep in mind, you can kind of disregard this. We're just looking at the values from x is 1/2 or -1/2 up until 2. So it's these endpoints that we're looking for. Draw your secant line through those, and there it is. When we go on to part C, what we're going to be doing is graphing, or looking at that secant line and then graphing a parallel tangent line to it. And this theorem states that there has to be an instantaneous rate of change that is equal to that average rate of change. So we will do that in the next step. Okay, so now we're on part C, and what we're looking for is a tangent line that's going to have the same slope as your secant line. And remember, the secant line is going to be the line that's drawn through your two endpoints on the interval -1/2 to 2. I actually just did this, and I accidentally did the interval from -1/2 to 1, so I'm starting over here. So if you kind of look closely, it's hard to tell, but the secant line is, or I'm sorry, the tangent line is the line that touches the graph at one point, and it's about right here that I'm interested in. At that x value, because that's going to be the line that I could draw through that one point of my function such that it's the same exact slope as my secant. So the first thing, how do we calculate that point? The first thing that we have to do is look at what is the slope of the secant line. So to do that, I am going to be calculating the change in the y's over the change in the x's. So I'm going to just plug in f of 2 minus f of negative 1/2. And then I'm going to put that all over 2 minus negative 1/2 and calculate this out. Understand that that will be a giant plus. So here I go. When I plug in 2, I'm going to get 2 over 2 plus 1. So 2/3 minus, and be a giant plus as well. 2 negatives make a positive. So up here too, I'm going to get, well, let's go ahead and 2/3 plus 3 over 3, going to be 5/2. So this is all equal to, I can go ahead and, since they're a common denominator, 5/3, 5/2. These cancel out. What I get is my slope is 2/3. Alright, so we have just found that the slope of my secant line, or the rate of change of this average change, is going to be 2/3. So there it is. So now what I'm interested in is, for what value of x, f prime of x, equal to 2/3. So to do that, I'm going to have to derive this. This is a quotient, so we are looking at the quotient rule. Here I go. I'm going to do low-de high, so x plus 1. To simplify this all out, by the way, this is what f prime is equal to. I'm going to get x plus 1 minus x all over x 1 over x plus 1 squared. And once again, this is the derivative that will get me the slope of all the tangent lines that you could possibly draw on this curve. So it's going to give me the tangent line at that point, that goes through that point of my curve, that goes through that point. But I'm specifically interested in the derivative with this specific slope, so I'm going to plug in that 2/3 that I got up from there. So what I've done is I've set f prime of x equal to that f of b minus f of a all over b minus a. And I got to solve for this. So this is what I have to solve for. Going from that step, I'm going to go ahead and solve for this by multiplying x plus 1 squared, to get this off the bottom, x plus 1 squared. These are going to cancel each other out. I'm going to get 1 equals 2/3 x plus 1 squared. Okay, so now, I mean, you could go ahead, and try to FOIL this all out and then do the quadratic formula because it is a quadratic. I'm just going to show you, I'm going to multiply this side by its reciprocal. So these cancel each other out. I get 3/2 on this side. I get 3/2 equals x plus 1 squared. So being that it's a perfect square, I can just square root both sides. I get plus minus the square root of 3/2 equals, and then x plus 1. So then I can just go ahead and subtract 1 from both sides. I get negative 1 plus minus the square root of 3/2 equals x. And then you just want to make sure to figure out which one of these falls into our interval. So if you go ahead and test this, oops, negative 1 plus square root of 3/2, and then negative 1 minus the square root of 3/2. Make sure that this is falling within the interval from negative 1/2 to 2, and what you're going to find out is this is the one that we want. So with that, our answer here for our secant line is going to be y equals, or I'm sorry, for our tangent line, negative 1 plus the square root of 3 over 2, and then x plus, and then the b, we're going to have to solve for that.